All right, welcome back. We are looking at relationships between Ka and Kb for this lesson. So let's consider the conjugate acid-base pair of ammonia and ammonium. So each of these species reacts like this in water. So let's write these out. We have NH4 plus reacting with water. In equilibrium, we've got our proton. We've got our acid here, we've got our proton donor, so I'm going to have NH3, so my conjugate base, and water will be my base, and my conjugate acid, H3O plus. We've got NH4, NH3, we have H2O and H3O plus. All right, now let's look at ammonia, NH3, where I take my conjugate base, bring it down here, and we can see my NH3. Here I've got my base, because this is my conjugate acid. Oops, I don't know why I put that 4 up there, NH4 plus. I have more hydrogens over here, so this has got to be the acid, therefore this is the base. So my water has got to be my acid. And OH negative is my conjugate base. So it wants us to express our Ka for the top equation. And we're just going to write the expression for this. So our Ka is our products over our reactants, leaving water out. So let's just write this. We have NH3 and H3O plus, my products over NH4 plus. My Ka. Let's look at my Kb. Again, products. So NH4 plus times OH minus, products over reactants, my NH3. Okay, so we've got the Ka for the top, the Kb for the bottom. Let's add the two equations together. Okay, so by adding the two equations together, we're taking NH4 plus. Let's take the left side of the top equation plus one water, another water, that's two waters, plus NH3. Okay, so that's everything on the left. Now let's take everything on the right. NH3 plus NH4 plus H3O, hydronium, and hydroxide. Okay, we've got our two equations added together. So do we see anything that can be simplified? Well, hopefully we see that NH3 and NH3 on both sides of the equation. So the ammonia and the ammonium can be simplified. Let's see what we're left with. And this should look familiar. So we've talked about how when two water molecules bombard, they dissociate, and we call this the ion product constant of water. When two water molecules dissociate, H3O plus and OH negative come out, and this is the ion product constant for water. We call this Kw. the equilibrium dissociation for water. So let's think back to what just happened. We started with two conjugate pairs, ammonium and ammonia. We showed in the Bronsted-Lowry theory their dissociation and how ammonium with its Ka and ammonium with its Kb, when added together, came right back to give us our Kw. In other words, we have a relationship. If this is the expression when we add Ka and Kb, remember that when we add equations, we multiply the K constants. So Ka and Kb is equal to our Kw. So there is our relationship between Ka and Kb. So continuing on with relationships, we just showed that Ka times Kb is equal to Kw. And Kw is equal to our H plus, or we can also write this as H3O plus. Remember, they're used interchangeably, times the hydroxide ion, which is all equal to 1 times 10 to the negative 14. Another relationship, pKa plus pKb is equal to pKw, which is 14. Here's another one, pH plus pOH, and this should look familiar, is equal to 14. So this relationship will come in handy when we want to convert a Ka into a Kb or vice versa. Let's look at this practice. So using Appendix D, make sure you have that handy. We're going to calculate the Kb for the fluoride ion. So let's just write this out. We'll call this number 1. We've got fluoride, F negative, and when mixed in water, forms equilibrium with, so this is going to be my base, my Bronsted-Lowry base. It's going to form its conjugate acid, and H2O is going to have donated that H, so we're left with OH negative. So here we have our conjugate base, and water is acting as an acid here. Now, to find the Kb, we would take our products over reactants, leaving water out. So HF times OH minus, we know it's our Kb because we're finding that hydroxide ion, that base ion, all over F minus. Well, we're not given any of the actual concentrations, so we can't actually find Kb this way. But what we can do is we can look up on Appendix D, hydrofluoric acid, HF, has a Ka of 6.8 times 10 to the negative 4. So Ka is 6.8 times 10 to the negative 4. And what we do know is that Ka times Kb is equal to Kw. And the constant, which means it doesn't change, the constant for this water is 1 times 10 to the negative 14. So what we can do to find Kb, we can plug in our Ka, 6.8 times 10 to the negative 4, make sure that's right, yep, times Kb. We can solve this by dividing both sides by 6.8 times 10 to the negative 4. And let's both plug these into our calculator to make sure that we get the same number. 1 times 10 to the negative 14 divided by 6.8 times 10 to the negative 4. We should get a Kb value of 1.47 times 10 to the negative 11. Remember, no units for our Kb value. All right, let's find the Ka for ammonium ion. So let's write out our expression. We've got ammonium, NH4, here's our number 2, NH4 plus, again, in water, forming a dynamic equilibrium, and we've got NH4. If NH4 plus is my acid and my base. So remember, my NH4 plus as an acid is going to give away one of my protons, so I will be left with NH3. I went from plus to neutral, and since this is donated, water's picking it up. H3O plus. So if NH4 is my acid, NH3 is my conjugate base, water is my base, then H3O plus would be my conjugate acid. So we are going to use our Appendix D, and we're going to look up ammonia, and its Kb is 1.8 times 10 to the negative 5. So Kb, 1.8 times 10 to the negative 5. And we want to find Ka. So we'll use that same idea when we say, well, Ka times Kb is equal to Kw. So Ka times 1.8 times 10 to the negative 5th is equal to 1 times 10 to the negative 14th. So I'm going to divide both sides by 1.8. Then we should get a Ka constant of, let's do the math here, 1 times 10 to the negative 14 divided by 1.8 times 10 to the negative 5th. I should get 5.56 times 10 to the negative 10th. And this is my Ka. So, an easy enough relationship. If I need a Ka turned into a Kb or vice versa, we'll use the ion product constant for water to do that exchange. Kw is equal to Ka times Kb. Continuing with our lesson, we'll discuss how salts act as acids and bases. This unit commonly is called the hydrolysis section. Hydrolysis as in adding water. We need to examine the way that dissolved salts can affect the pH. Now let's remind ourselves of some of these chemical families that we've been using. In this chapter, acids start with an H, proton donors. Bases end with an OH, they're proton acceptors. And they produce in water, after they neutralize one another, salts. These are ionic compounds. Salts are always strong electrolytes, if indeed they are soluble. Strong electrolytes always 100% dissociate. If an acid, and let's just use the generic formula, HX, H, our acid starts with an H, reacts with a base. Let's just put metal hydroxide. This is our acid. So we have our acid and our metal hydroxide. Any metal like lithium, sodium, potassium, anything like that would work for the metal. So this is an acid-base neutralization. We will make a salt. We will have our metal, our positive, our X, which was our anion. This is our salt. And then, of course, we'll have water. This is the product of our acid-base neutralization, and it may affect the pH of a solution. So we have to discuss how we would know many cations, and here's the cations of a base, that's the positive ion, so right here, many cations and anions, that's the negative ion of the acid, are able to react with water to regenerate either the acid proton or the base ion. And this reaction is what we call hydrolysis, simply adding water. So sometimes the positive ion from a base can react with water. Sometimes the negative ion of an acid can react with water. And if they do so, they will end up affecting the pH. Let's talk a little bit further about how we would know whether or not this reaction occurs. Okay, so when we were just talking on the last slide, X negative is the conjugate base of an acid. So when we said HX this is our acid, right? Like hydrochloric acid. So it's going to break apart into H plus and X negative. This X negative is the conjugate base of an acid. For example, chloride, Cl minus, is the conjugate base of HCl, right? If we have HCl, we'll split into H plus and Cl minus. So these are conjugate pairs, HCl and Cl minus. This is my acid. This is the conjugate base. Another conjugate pairs, acetate from acetic acid. Again, here's my acetic acid. It's going to break apart into H plus and C2H3O2 minus. Okay, so this is the acid. This is the conjugate. Oh, sorry, just kidding. This is the acid, starts with H, duh. And this is the conjugate base. Now, if X minus comes from a strong acid, right? One of those top 7 that we've memorized, like HCl. So that chloride, any of those top 7, it will not affect the pH of the solution. No effect. However, if that anion comes from a weak acid, we know weak acid is anything on our Appendix D, anything that has a Ka. So like sulfuric acid, no. H2SO4, so if it was sulfate, no, that's a strong, that's one of the top 7, that will not affect. But if it's any of those other ones that have a Ka constant, those are weak acids. So if our X negative comes from a weak acid, it will abstract a proton from water, generating a hydroxide ion, and it will affect the pH. Let's look at a couple of these examples since we have 2 of them right here. So let's look at HCl. We know that this is a strong acid. And let's say we add some water to it. We know that if it's strong, it's going to 100% dissociate. There is not an equilibrium here. And it is going to create all H3O plus ions and Cl minus ions. And there is no effect on the pH. All right, we have chloride ions that are our other product. So, no effect. All of that HCl is converted into our hydronium ions and chloride ions. There's no effect on the pH. Let's look at our other example, acetic acid. So we have HC2H3O2 in water. We know that this is a weak acid. How do we know it's weak? Well, it's not part of the 7 that we memorized, and we can find it on here. On our Appendix D, we have acetic acid. There's a Ka constant to it. We know that all of these that have Ka constant values are weak acids. All right, so we have an equilibrium, therefore, and we know that we have H3O plus and C2H3O2 minus. So, and we just said up here that if this X minus, so this acetate, comes from a weak acid, and we know our weak acids are going to form equilibrium, it will affect the pH. And let's see how. Will because of a process called hydrolysis, which means that we are reacting with water. That means we are taking our X minus, that base, this, that will affect the pH. We are reacting that base, because this is our acid, this is our conjugate base. We're taking that base, reacting it with water. Let's see what happens. C2H3O2 minus. So we have our base with water. So therefore the water in this instance is our acid. All right, we're setting up an equilibrium. Let's form our conjugate acid, which we know is acetate, HC2H3O2. So this is my conjugate acid plus the conjugate base of water, right? This donated the proton, so we now have OH minus. This is the conjugate base. So this right here, this product of our X minus from our acetic acid reacting with water is in equilibrium, and it is creating that hydroxide. This is what is making our solution more basic. It will affect the pH. So we can generalize and we can say when the conjugate base of a weak acid undergoes hydrolysis, the solution becomes more basic. We can also say that it's becoming less acidic, if that helps. And if we go back and look at our reaction here, if we think of Le Chatelier's, when I have my weak acid and it's forming this conjugate base, we know it's going to affect the pH. And when we push back and go to the left, we will use up our products to create more reactants. So that means our H3O plus is going to go down when I am pushing back left. So that means less acidic there. So less acidic and more basic again. And then when we undergo hydrolysis, and I take that conjugate base and it creates hydroxide, this makes it more basic. Let's look at another example. We just did this first one. Well, this is just kind of a generic look, and we just did acetic acid on the slide before. So let's look at this example. What effect will each of the following ions have on the pH of a solution? We've got nitrate and carbonate. So let's look at nitrate. Nitrate is NO3 minus. Okay, so we need to, and this would be a product, NO3 minus, and so we need to think, what was its parent acid? HNO3, right? So this is my acid, this would be my base. And of course we have our water acting as our base. So this is our acid, our conjugate base, H3O plus. Okay, so what would this have on the solution if I have nitrate, which is right here? Well, we need to be able to look at that parent acid and go, ooh, HNO3, that is part of the big, strong 7. And we said, if it was part of the strong 7, it's going to have no effect on the pH. Of that solution. No hydrolysis will happen because 100% of that HNO3 dissociates. So no hydrolysis, no effect. Got to know that for that strong 7. Let's look at our second one, carbonate. So carbonate, oh, so there is no equilibrium here. This is just going 100% to the right. So our second one, we've got carbonate, CO3, 2 minus, and its parent, let's say, I don't know if this is going to be equilibrium or just full one direction. So let's see, its parent would be HCO3 minus. And so this is the acid, this would be the conjugate base. So then that would mean I would need water as a base. So water's conjugate acid would be H3O plus. All right, so we want to know about carbonate. So let's look at carbonate's parent acid, HCO3. And is that part of the big 7? Well, if you aren't sure, it should not be. Kind of like this, nitric acid. Do you see nitric acid on our appendix? Nitric acid, no. Nitrous, yes, that is not the same thing. No nitric acid. However, do we see carbonic acid? Yes. Now this is H2CO3. That means it's diprotic, so it would have 2 Kas, and just the HCO3 would be using the second Ka. So it is a weak acid. Weak acid means that this is going to go through hydrolysis. That means that it is going to push back. So we are going to be in equilibrium. It's going pushing left, it's pushing right. And when it pushes back, it's going to use up some more of my H3O plus. It's going to use that up, make this less acidic, and it's going to then go through hydrolysis. Let's see what that looks like. So it's going to use my conjugate base. So it's going to take that CO3, 2 minus, react with water. Now this conjugate base, and when it goes through hydrolysis and combines with water, it's going to, now this is acting as my, this is my conjugate base comes down here to act with water. It's going to grab, my water is acting as the acid, it's going to grab another H, become HCO3 minus again. It's going to regenerate back to the parent acid, leaving water, since it just donated, with OH minus. That's our conjugate base here. Because of this hydrolysis, having my conjugate base react with water to form the parent acid again, which is great. We want to form that parent acid, right? This is equilibrium. We are pushing left. We're forming that parent acid again, but we're also adding this hydroxide component to it. This hydroxide is going to make it more basic solution. That's because we had a weak acid, and a weak acid is going to go through hydrolysis. So that conjugate base is going to be added with water to reform its parent acid and hydroxide. So we've been looking at the negative ions. Now let's look at the positive ions. So one of the most popular one, or most common one, for polyatomic cations whose formulas contain one or more protons can be considered the conjugate acids of weak bases. And NH4 plus ammonium is the most common one. And we can see that when that undergoes hydrolysis, so adding with water, we form the base ammonia and H3O plus. So this makes a solution more acidic when this undergoes hydrolysis. Most metal ions can also react with water to decrease the pH if it's from a weak base. Cations from strong bases do not affect the pH. So similar to the last slide when we talked about the 7 strong acids, how it didn't affect. Now, if it's a strong base, it does not affect the pH. So let's remember what our strong bases are. We said it was the first column, my alkali metals, lithium hydroxide, sodium hydroxide, lithium, sodium, potassium, rubidium, and cesium. In my second column, we said calcium, strontium, and barium. These are not going to affect the pH, but any other ion, any other cation that is,